of each other?
Okay, so are you predicting that they'll go out, or you're just doing the generically opposite of each other?
I'm thinking just generic, like opposites.
Okay.
Yeah.
They will definitely go opposite of each other. Why? Why do we, before we do anything else, why do we know those wires will go opposite of each other?
Well, they're creating opposite electric fields, or magnetic fields for the other. Like, it'll be coming out of the board from wire 1 in the middle between them. It'll be going into the board with wire 2. So like the part of the middle will have 2 opposite.
Okay. So we'll get some multi-color effects here. So that one's going down like that. So this creates a magnetic field that's going into the board here, out of the board over here. So we'll do purple for this one, or whatever color this is, or not. That was into the board. Trying to give some sense of the fact that it weakens the farther out you go.
Okay.
And this is the same current, so it does the same exact thing. There will be dots like in between the two.
All I've done is just the magnetic field from this wire right here.
Right. I'm saying for I1, it's going to have a similar.
Oh, yep. So for I1, it's going into the board over here and out of the board over there. So into the board over here. And out of the board over here. Now, similar to a charged particle is not going to feel its own electric field, the wire is not going to feel its own magnetic field. Yes, I can come up with a configuration where it does that. For right now, let's assume that's not possible. So wire 1 is blue. All right, so wire 1 is going to experience the purple. So which way will wire 1 be forced? If the magnetic field it experiences is into the board and the current's going down. Everyone should have an answer. I only see 2 people doing the hand maneuvers. There are 3 people doing hand maneuvers.
Could you repeat the question again?
Yeah.
All right, so this wire 2 here is creating the purple magnetic fields into the board over here, out of the board over here. Wire 1 is feeling that magnetic field that's going into the board here. Which way will wire 1 be forced with its current going down and the magnetic field going into the board?
Out this way?
Can I use stem gun here or no?
Yeah, you can do spin gun, just your finger points in the direction of the current.
That always like help me kind of figure out direction, I feel like. When something's getting pushed, the stem gun for some reason.
Okay.
I don't know why.
Okay, I'm confused because when I'm doing it, I feel like I'm actually getting this direction because the electrons are moving up. So your fingers have to point in the direction of the electrons, but they should curl out of the board. But since they're electrons, it's the opposite direction, so it should be this way.
Doesn't your thumb go in the direction of the electrons?
It should. Oh, your thumb? That was your fingers.
Well,
I'm
that's the-
so confused, Dr. Fox.
The downside of the number of right hand rules. All right, so
If I stem, is it going this way? Is that right? The current going this way?
magnetic field's going into the board.
Oh, okay.
So
Your finger needs to go down, but your
fingers going down.
Uh-huh.
These fingers right here are heading into the board.
Okay, to the right.
So it is to the right.
Yes.
So this is going to be forced that way.
I was
Okay.
gonna say, because
Yeah.
it's like opposites attract, I was confused because you said they're gonna go opposite directions, but since there's both like into the board and out of the board happening in the middle, I think that like opposites would attract and they would like get closer.
What are the? Oh, I hesitate to do that because I'm thinking what's opposite because the currents are flowing in the same direction. So
Yeah, right.
be careful about that wording. Yeah, this one will be sucked that way. Let's make sure we understand why, or at least can resolve it. So this current's flowing down. The magnetic field over here, the blue dots that are coming from that wire are going out of the board.
For the board. Yep, Sten gun. I'm telling you guys, you gotta start using the Sten gun.
Okay, but it doesn't work for everything.
I know,
I think
just with direction, Brooke.
Okay.
The other reason why they have to be going in opposite directions, Newton's third law. This is the force that wire 2 exerts on it. This is the force that wire 1 exerts on wire 2. The force that wire 2 exerts on wire 1. They better be in opposite directions. If they're in the same direction, that means I can keep a magnetic field with 2 wires on it, and then run current through them, and then they'll start drifting together. Which is kind of creepy when I think about that. You probably can weaponize that somehow. Because you got the Earth's magnetic field. You just get some really light materials and get them, put them together, and suddenly they're just shooting off.
What was the saying? You said at one time, the phrase you said about physics and developing weapons.
All physics leads to weapons.
Yes. Yeah.
So if I had those currents going in opposite directions, what would happen?
You're good at the opposite.
Let's see that happen. All right, I do need a little bit of prep time here. I'm going to pause this. And this is, I consider this the coolest demonstration that I do.
Nice. Film this for my own posterity.
Oh, absolutely.
This is
But if this doesn't work, then we know it's you that have cursed it.
mind blown.
After this semester,
ready to
we
go.
won't have access to these lectures, so we won't ever get to see it again unless we film.
All right, here we go.
Wow. That's cool.
To me, that is wow.
That was awesome.
Do it one more.
Can we do it
Wait, did
again?
you turn
Can we do it
it
Now-
again?
Now what happened, I didn't turn it, oh, I did turn it off, but it. Okay, I haven't turned it off.
Oh, man.
Whoa. No way.
The reason why it puffs out when the current flows through it, and the reason why it then stops is, again, circuit breaks, there's no more current flowing through it, and it goes back to normal. So right now the current is
Yeah,
broken.
I saved it.
Oh, yeah.
So when you do the experiment, you get that brief moment of you'll be watching it
Take that with you
and
the
be
rest
able to
of your
get how far apart do they actually spread. And, you know, if you miss it, then you gotta do it again, and it's just as simple as hitting the button here.
Whoa.
So in the lab, we have to like look at how far apart it's spread, and then we're like, okay, that's like we have to measure that.
Yes.
Oh, okay.
So you'll have something behind it just so that you
Can
know,
measure. Yeah.
you'll see it. And at least today, you film it with a camera, film it with your phone, and then you can go back through and get much better measurements than how it's been so many times in the past.
Oh my gosh. It's amazing. It's excellent. It's
It
beautiful.
is,
It's
and despite the
It
fact
is
that
cool.
I'm sensing some sarcasm from some of your comments.
Not me.
It really
Not-
is.
no.
No,
That was
I
awesome.
actually
Okay.
do think it's pretty cool.
Okay.
I
Yeah.
think we're over exaggerating a little bit though. We're like, oh my gosh, wow.
Right. We're being playful.
Well, also
It's
note,
cool.
it is a physics demonstration that worked. So
Yes.
Very true.
Yeah.
yeah, it's a rarity.
Did you expect it to only like puff out for a brief second, or did you expect it to stay out?
Considering the number of times it just sort of twitches, it twitched in the past, I've never, like mind's eye, I don't expect it to puff out as much as it does right there.
Can I press the button?
Can I press it?
Come on up, press the button.
Alright, alright.
Step up, step up.
And if he gets electrocuted,
Oh, yeah.
we will erase this film.
All right,
Recording.
Harrison.
Is everyone ready?
The DC
Yeah,
breaker.
so ready.
I'm going to hit the DC breaker button.
Oh my god.
Thank you.
Wow.
Thank you.
Sounded so dumb.
Legend.
That was awesome.
So now, because physics is not complete unless we have an equation, let's do the equation.
And here.
Now the equation is not something brand new. We're just going to be using stuff that we've already have had on the board. Most of it's erased now. And for those watching at home, sorry about that, the seasickness there. So let's take a look at the magnetic field that's acting here. I got a long straight wire. We'll assume infinitely long for the moment. The distance between them, we do need something for that. So D for distance. So know that the magnetic field created by 1 is equal to mu naught times I1 divided by 2 pi, not R1, D. So that's just the magnetic field that is created by the current number 1. I know that the force on 2 from 1 is equal to the current times L cross B1. I guess it's I2. So that is going to be the force that is acting on wire 2. Because they are parallel to each other, we really don't need to worry about the cross product. For the parts that are parallel, the magnetic field will be perpendicular to the wire itself. And so we can just look at the magnitude of the force, which is I2 L2 B1. And now we'll just substitute that in. So I get mu naught I1 I2 L2 over 2 pi D. So just took that, substitute in for B1. And we're really caring about the length that they are parallel to each other. So this, I wrote L2 here, but really it's the same as L1. The length is going to be the same. So I'll just get rid of that subscript. And then the more traditional way of writing this is force per length instead of just force is mu naught I1 I2 over 2 pi times the distance between them.
So the reason we're using 2 pi d is because d is like our radius of the circle of magnetic field that's creating that wire.
Yes.
D has nothing to do with diameter. It's like saying 2 pi r, but r, the radius of that circle in this case, is the distance between them.
Correct. And the reason why I didn't want to go with R here is that I don't want you to think of radius of the wire. It has nothing to do with radius of the wire.
Wait, so the D is the diameter?
So D is the distance between the two wires.
Okay.
So let's just do a quick plug and chug. So let's go with 5 amperes and 10 amperes. And let's put 3 millimeters apart. That would be center to center distance. And so the force per length is 4 pi times 10 to the negative 7 Tesla meters per ampere times 5 amperes times 10 amperes divided by
5.003.
0.003. That would be meters.
And that gets us the force from, wait, what does that give us?
That would give us the force per unit length.
So it's 3.33 times 10 to the negative third Teslas? Not right.
Not Teslas.
Well, this is the force? Oh, I'm
So
sorry.
newtons.
Tesla newtons?
Let's drop back again. What do we find?
Here, I can do this.
Yeah, this is your thing.
This is going to be Tesla amps. No. Yes, yeah. Yeah, Tesla amps.
Okay. Sure. What would be a more traditional unit for it?
I don't know. I know that. I
Force
mean,
per unit.
newtons.
So it's newtons per.
Where does Newton come in?
No, I like
That's
Tesla.
force. That's the only thing.
All right, so I've heard newtons, and I've heard force per, and then there's a trail off.
Force per unit length. That's what you
So
said.
therefore, the unit, more traditional unit would be
Newton.
Newton per
per meter.
Newton meter.
So the question is, how is a Tesla ampere the same as a Newton per meter?
Yeah, what is, that's what.
Maybe it's not, maybe it's all a lie. Maybe there's a careless error somewhere. I hope not.
Maybe a Newton is actually a Tesla.
Maybe a second is actually an ohm meter, whatever.
Oh my
There are
gosh,
some
yeah,
really
yeah.
bizarre
The,
relationships
like,
there.
ohm joule
Yeah,
per volt.
how'd you feel about that one, Harrison? Was that like all you?
No, it wasn't. I thought it was. I saw it.
It's a major rail.
I saw it, and I was like, "Oh, this question was made for me, and
Yes, it was.
I couldn't do it."
It was a major rail.
All right, a joule is a Newton meter. That, if you go back to work, is equal to force times displacement. So the equation work is force times displacement. There are other ways of getting there, but Newton meter. I also know that a joule per coulomb is a volt. Let's see how I want to get there. And, oh, I know that, and this is from the delta U over Q is equal to delta V. That's the equation. But also know that, see, if somebody just said newtons per meter to start out with, we would not be going down this rabbit hole, but we did.
Well, on a test, would Tesla
helpful to know
amps
how.
be acceptable as an answer?
It's what?
Tesla amps. I don't know how to. I never know when it's the dot when it's Tesla times amps. Would
Just
that be
make sure you say it as separate words.
okay?
So
Tesla
amps.
Tesla amps. Would that be an acceptable unit on a test?
Yeah, probably. Assuming that if this works. So now I have a Newton meter per coulomb is equal to a volt. And I know an ampere. I know that delta V is equal to IR, so a volt is an ampere ohm. Not necessarily the way I want to go, all right? Oh, wait a second, I need to get newtons and Tesla in the same thing. F is equal to QVB. So that would be a Newton is a coulomb meter Tesla per second. There we go. A coulomb per second is?
No idea.
I should know.
Yeah, I'm hoping all of you know.
Coulomb per second.
Charge over
Charge over
That's-
time. We just said that.
I know, we
What's
just
charge
went over
over
this.
time? That's
With-
current.
That's
Yes,
correct.
it's current.
Oh yeah.
Which has units of amperes.
Yes.
So this becomes an ampere meter Tesla. And if you divide by meters, you get a Newton per meter on the left side and ampere Tesla on the right side. Done.
Done. Bang.
Harrison, you should have been able to do that.
So,
That was for you.
Uh,
That was like a-
so what would happen on a test is I'd be expecting newtons per meter, suddenly I see Tesla amperes, and I'm going, oh, all right, let's find out if that works. Okay, yeah, it works. Okay, now I'm good. Then I'll make a little note so the next person does Tesla amperes.
Nice. That's what
Not
I
fast
would do.
enough. I won't do the honor roll for the second person. Are we done with 30? Let's just say not, since we do have class next week. So Monday we'll finish up 30.
So we don't have class. Is spring break next Wednesday? Is that right?
Yeah, there's no class on Tuesday either. Spring break officially is Wednesday, Thursday, but you don't have class on Tuesday. So you get, the long middle of the week, all 3 days
Yep.
of
Then we're back
vacation.
on Friday.
So we're here, classes on Monday and Friday.
Anybody who wanted to take like a week trip,
Yeah.
like has to be here for Friday, which I think is funny.
Yeah, Yeah.
Whatever.
I'm not part of the scheduling group, and I'd still imagine it's a nightmare to schedule it all.
Speaking of,
I do want to point out that one of the reasons I'm wearing this shirt today is
great shirt.
bringing back Fun Shirt Friday.
Yes.
So Fun Shirt Friday, don't forget, next Friday.
You know, I'm kind of in that, like, I'm golfing later today, but this is pretty fun.
Okay.
Yeah, the little Nike symbols everywhere.
Look, they're flag posts.
I thought they
I
were
noticed
Nike
it. At first I thought they were
symbols.
Nike, but then I saw it's the flag.
Or the vector symbols, I can't
Yeah,
quite
for
tell.
golf.
For golf.
Oh.
Isn't this
See,
pretty
I
cool?
saw the like Callaway logo and I was like, why would they put Nike symbols
Symbols
all
on the,
over
oh,
it?
yeah. But I'm with Fun Shirt Friday. I'm with
All right,
that.
Fun Shirt Friday. Also, I've noticed a generational difference between what I consider a fun shirt and what students consider fun shirts. We'll see if that holds.
Well, I can only wear what I wear to work, so it doesn't matter.
Yeah.
Yeah,
You
what
could
the hell
change.
am I
You
gonna
could
wear to
change,
work?
Wesley.
Yeah.
You could really put
I
your
can
heart
tell,
into
tell
it.
them I'm gonna wear whatever I
There's a bathroom right over there, brother.
That's
All right.
true.
Three
No,
shirts.
no excuse
Two
me.
shirts.
Shirts, yeah.
I assume Anna will show up in fun blue.
I might, but I'll try my best.
I will
I
not.
could change.
Anyone who
I
doesn't
can't.
participate in Fun Shirt Friday will be getting ostracized.
I won't be participating in class. Like I'm not gonna be.
All right.
So I can't
And-
participate.
And anybody need to desperately get out right now? I'm gonna try something that's gonna take a couple minutes.
No, I mean, not.
All right, if you're good with it. All right, counting to 10. I haven't done counting to 10 with this group yet, right?
Okay, I don't think so.
Oh, like each of us.
Here are the rules.
I'm so afraid of
Oh, no.
As a group, you're gonna count from 1 to 10. You're not allowed to do any two numbers in a row. You personally are not allowed to do any two numbers in a row. You can't point to anybody who's gonna do the next number.
Ooh.
And if any number is repeated, start over.
Just a 10.
I like it.
Just a 10.
Yeah.
All right,
We can't shout it out, we just gotta go. You just gotta go. Or-
somebody's gonna eventually say the number
One.
1.
2,
3, 4,
5, 6,
0, 8, 9.
10.
Wow.
First try. First try.
I started with 1 and wasn't saying anything.